Okay, dear students, we'll see what is shear force and bending moment diagrams. What is a shear force diagram? A diagram in which ordinate represents shear force and the abscissa represents the position of the section is called a shear force diagram. And what is a bending moment diagram? A diagram in which ordinate represents bending moment and abscissa represents the position of the section is called a bending moment diagram. Okay, so this is a bending moment diagram. How will you find what is the meaning of shear force at a section? Shear force at a section in a beam is the unbalanced vertical force that is trying to shear off the section and is obtained as the algebraic sum of the forces including the reactions acting normal to the axis of the beam either to the left or to the right of the section. So what is bending moment? Bending moment at a section in a beam is the moment that is trying to bend the beam and is obtained as the algebraic sum of the moments about the section of all the forces including the reactions acting on the beam either to the left or to the right of the section. Now what are the informations that have to be shown in a shear force and bending moment diagram? You have to show all the values at all salient points, that is important points, that is the points where values are maximum or minimum and the points where nature of variation changes. And you have to show what is the nature of variation between the salient points. And you have to show the location of point of contraflexure. What is the meaning of point of contraflexure? That is the point where moment changes its sign. At this point, bending moment is 0. Okay. Now you have to first draw the shear force diagram and bending moment diagram for standard cases. Now you have to represent shear force diagram short form as SFD and bending moment diagram short form as BMD. So you have to consider the following standard cases. You have to draw the bending moment and shear force diagram for cantilever subjected to concentrated load at free end, cantilever subjected to uniformly distributed load over the entire span, uniformly varying load over the entire span, and in the case of simply supported beam subjected to a concentrated load, simply supported beam subjected to uniformly distributed load over entire span, simply supported beam subjected to uniformly varying load over entire span, and a simply supported beam subjected to an external moment. Then you have to study about the overhanging beam subjected to a concentrated load at free end. So first we'll see how to draw the shear force diagram and bending moment diagram for a cantilever subjected to a concentrated load at the free end. So you consider this cantilever, it is subjected to a concentrated load W at the free end, W kilonewton acting downwards at the free end. So you first of all you consider a section line XX at a distance small x from the free end. So what is the unbalanced force to the right of the section line? F is equal to W. So our sign convention is to the right of the section all the forces acting downwards is positive. So here the shear force at this section is W acting downwards, so plus W. So you can see there is no other load other than this W acting at this point. So there is no change in the load throughout the length of the beam. So the shear force is constant at any section and its value is equal to plus W. Okay. So we can draw the shear force diagram. We are usually drawing the positive sense of the shear force above the x-axis. So it is positive. So this is the line showing the center line of the beam. So we are drawing the ordinate along the y-axis. Let this be W and it remains constant up to this support. So it is W. So this is the shear force diagram. Since it is right downwards, it is positive. Now let us find out what is the bending moment. Now let us see how to draw the bending moment diagram. So whenever a cantilever beam is subjected to a load like this, at a point load at free end, this will bend like this. So as a result, what will happen? You can see when there is a bending like this, there will be tension at the top and compression at the bottom. So as a result, we have early seen that whenever you are drawing a bending moment diagram, you are drawing the bending moment diagram on the tension side. So since here tension is on top of the beam, let us draw the bending moment diagram on the top of the center line of the beam. Okay, so that's why we are drawing the bending moment diagram on top of this center line of the beam. So what is the value of bending moment? Bending moment is load into distance. So you consider the section line XX. So at section XX, what is the bending moment? W into load into distance, W into X. So this is producing a clockwise moment about this section. It is right clockwise. So our sign concept is right anti-clockwise is positive. So right clockwise is negative. So it is minus W into X. Now we have to find out what is the value of bending moment at this point B and A. So what is the value of bending moment at this point B? At X equal to, here we are taking X towards this side. So here at X equal to 0, that is at B, X equal to 0, this when you substitute in this equation, bending moment equal to 0. Now what is the value of bending moment at X equal to L, that is at A? We are taking X from B to A. So at X equal to L, bending moment equal to minus W into L. So this is varying linearly, W into X. So we can draw this ordinate as 0 and this as WL. Joining, you will get this diagram, a triangular variation. And we are drawing the bending moment diagram on the tension side, and this is negative because you have a hogging moment. Moment is hogging because right clockwise it will bend like this. So it is a hogging moment. So it is negative bending moment. Okay, now let us see how to draw the shear force diagram and bending moment diagram for a cantilever subjected to uniformly distributed load. You consider a cantilever like this of length L subjected to uniformly distributed load of W per meter length. So you have to first draw the shear force diagram. So what is the equation for shear force? We are taking the sign convention as right downwards positive. So you consider a section line XX at a distance small x from the right support. So what is the shear force? Shear force is the unbalanced force to the right of the section. What is the unbalanced force? W into X. So what is the value of shear force at X equal to 0? Now we substitute when X equal to 0, you will get the shear force at this point at the free end equal to 0. Now what is the shear force at X equal to L, that is at the fixed support? Substituting X equal to L, you will get the shear forces plus W into L. So here you can see the variation is linear. Shear force varies with X linearly with X, so it is linear variation. So you can draw the shear force diagram like a linear variation 0 to W into L. Now we'll see how to draw the bending moment diagram. So in order to draw the bending moment diagram, what is the sign convention we are taking? Right clockwise is negative. So you consider this section. What is the bending moment about this section XX due to this load W per meter length acting downwards? So this W is the load intensity. So for X distance, the load will be W into X, and it will be acting at the center of this X meter span, that is at X by 2 from the right support. So the moment about this section line is W into X by 2. So this is right clockwise, moment about the section line is clockwise moment, so it is negative. So we can write it as minus W into X square by 2. Now we can see the bending moment varies with X square. So the variation is parabolic variation. Here the variation is linear variation, while the bending moment is parabolic variation because the equation is minus Wx square by 2. So we can write here, when we substitute at X equal to 0, what is the bending moment? At X equal to 0, bending moment is 0. So at this free end, bending moment is 0. Now at X equal to L, let us substitute here x equal to L. You will get minus W into L square by 2. So we are drawing the bending moment diagram always on the tension side. In a cantilever, tension occurs at the top, so we are drawing it on the top. 0 to WL square by 2. It is negative because it is producing a hogging moment, and the value is WL square by 12, maximum bending moment, hogging moment. So it is negative. Okay, now let us consider what is the bending moment due to a cantilever beam subjected to uniformly varying load. So you consider a cantilever beam like this. It is subjected to uniformly varying load, a triangular loading, varying the value is 0 to maximum value W per meter length. This ordinate is W per meter length. So how can you write the equation for shear force? Shear force is the unbalanced vertical load to the right of the section. You consider a section XX at a distance small x from the right support. Now in order to find out what is the unbalanced load due to this much portion, you have to consider what is this ordinate on the section. You have to find out what is this ordinate. In order to find out this ordinate, we can take the similar triangles. That is W by L, this whole span is, let this span be L. W by L is equal to Wx. Let us take this ordinate as W suffix x, Wx by x. So we can write this ordinate as Wx equal to W into x by capital L. Now we can find out what is the unbalanced vertical force to the right of the section. This is equal to area of this small triangle. What is the area of this triangle? Half into base into altitude. What is the base? Base is W suffix x, which is equal to W into x by L. So substituting here half into Wx by L into x, this becomes shear force equal to Wx square by 12. Now we have to find out what is the value of shear force at x equal to 0. When we substitute x equal to 0, you will get the shear force is 0. That is the shear, in the shear force diagram, the value at the free end is equal to 0. Now we have to find out what is the value at x equal to L. Substituting here x equal to L in this equation, we will get the shear force equal to WL square by 2L, which is equal to WL by 2. So the maximum ordinate is WL by 2. Now here you can see the equation for shear force is Wx square by 2L. So this equation varies with x square, means this is parabolic variation. The variation is parabolic. Now you consider this, we have to draw the bending moment diagram. In order to draw the bending moment diagram, we have to find out what is the bending moment at the section XX. So what is the bending moment at the section XX? You know what is this ordinate now. This ordinate at the section is Wx square by L. So the area of this small triangle is half into Wx square by L, and it will be acting at the centroid. The centroid of this small triangle will be at a distance of 1/3 of x from this portion, the section line. So 1/3 of x. So you will get the equation for bending moment as minus Wx cube by 6L. Now let us substitute what is the value, find out what is the value at x equal to 0. At x equal to 0, when you substitute in this equation, you will get m equal to 0. Now we have to find out what is the value at x equal to L. When you substitute in this equation x equal to L, you will get the value for bending moment equal to WL square by 6. WL square by 6. Okay. So now you have got the maximum value for bending moment as WL square by 6, and here also you have to draw this diagram, bending moment diagram, on the tension side. So in a cantilever beam, the tension is at the top of the beam, so we are drawing it upwards. This is producing a hogging moment, so we are taking it as negative moment. So you have got the bending moment diagram as a cubic variation. Now you know the equation is minus Wx cube by 6L. So the variation is cubic variation, so you have to draw it like this. So this is how you have to draw the bending moment and shear force diagram for cantilever beams. Thank you.